In this video, we will discuss the Poisson distribution and some properties associated with it. So the main thing that we want to keep in mind between our binomial distribution and the Poisson distribution is that the Poisson distribution is used to describe events that occur in time or space. Now, just as we had conditions for the binomial distribution, we have conditions for the Poisson distribution. There's three conditions that must be met. The first condition is that the average rate that events occur is the same at all times, so kind of an equally distributed idea. 2, the number of events that occur in non-overlapping time intervals are independent from each other. And then 3, for a very short interval of time, we must have 1, that it is impossible for more than one event to occur within the time interval. And 2, the probability that one event occurs in the interval is approximately equal to lambda times t, where lambda is the average rate at which event occurs, t is the time. Now here we're going to quickly go over the differences between Poisson and binomial. When we use binomial distribution, there's going to be a fixed number n of trials, and we count the number of trials that result in success. When we use the Poisson distribution, we count the number of events that occur in a given amount of time or space. Let's get to some of our examples and see how we can use this Poisson distribution. So if we know that we're dealing with the Poisson distribution, then we have the formula that gives for a Poisson random variable x, then the number of events occurring at an average rate lambda. So lambda is our average rate. The events occur. We see lambda here in the formula, also here, and a time interval of length t, here and here. The probability that the events occur is given by this formula, and here we want to keep in mind this e is that constant, which is approximated to the first few decimal places, 2.71828 when rounded. Now, e is actually a number that has infinitely many decimal places, and you don't use the rounded version, you use the button e in your calculator. The possible values of x, they would then be 0, 1, 2, and 3, so once you know the x value that you're looking at, that's what gets replaced here. We've got an x factorial on the bottom of the fraction, and an x here is the exponent. So using this formula, we will be able to calculate the probability that x events occur in a given period of time. So I'd encourage you to make sure this formula is definitely labeled on your note sheet for your upcoming exam. We'll need to have this written down so that we can use it in our homework and exams. So here it says a grandmother bakes chocolate chip cookies in batches of 100. She puts 600 chocolate chips in each batch so that the number of chocolate chips in a randomly chosen cookie has a Poisson distribution of lambda equal to 6. Where did we get that 6? It was from the 600 divided by 100. We're asked to round our answers to 4 decimal places. So in part A, it says you get 1 cookie. Now in this case, remember they said time or space. So the fact is when we get 1 cookie, we're only looking at that one sample. That's our t. So here, it's not that time is 1, but t represents our time or space, our unit that we're looking at. So we're looking at 1 cookie. What is then the probability that it contains exactly 8 chips? So here the number exactly 8, that's our event we're looking for when x is 8. Now they told us that we could use the Poisson distribution. So that means this formula will work for us. So let's see if we've got everything we need. To use the formula, we need to know what's the x value, it's 8. We need to know the lambda value, which is 6. We need to know our t value, which is 1. And we have to know how to use e in our calculator. We've got all of that, so let's write out the formula. So this will be that the probability for this Poisson distribution that we have 8 chips in the single cookie is the probability of 8 is equal to e. Remember that letter represents that special number that you can find in your calculator, minus lambda is 6 times our time period here, or space and time is 1, times parentheses lambda is 6 times the space here again of 1 to the 8th power over 8 factorial. Let's color code this to match our formula above. And I know whenever I type things into my calculator, if my exponent has a lot going on, I want to simplify and then mark it. So here, 6 times 1 is 6, times negative 1 is negative 6, so that's e to the negative 6, which I'll offset in parentheses, times 6 times 1 is 6, so that's 6. Remember, this is not 61 or 6.1, but 6 times 1 to the 8th over 8 factorial, which I'm going to write as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Typing this into the calculator, and we'll get... Now, the order that I have to type things into my calculator might be different than yours, but the idea here is I find my button E, I say exponent to the negative 6 times the top of my fraction should be in parentheses, bottom of my fraction offset in parentheses, write it so I don't forget, times 6 to the 8th, close parentheses for the top fraction, divided by 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, close parentheses. And when we calculate that, we get exactly this value. They said round to 4 decimal places. We look 2 is the 4th, pass it as a 5, that means we round up. This should round to a probability of 0.1033. So that's our first example working with this formula. Let's look at part B. So it's got the same basic setup from before, except now what's changed is we've got 2 cookies. What's the probability the 2 cookies combined will have a total of exactly 15 chips? Now think through what's changed here. Now that we have 2 cookies, our space that we're looking at is 2. And now that we're looking at 15 chips in total, that's an x value of 15. Now from before, the lambda is still 6. We've got the same formula for the probability for our Poisson distribution as before. I would encourage you right now to pause the video and write out the expression for the probability of 15 using the formula. Unpause to check your work. So here, as before, we start writing out the basics. It's e to the negative lambda times t times lambda times t to the x value in question, which in our case is 15, divided by 15 factorial. Now I'm going to simplify this before I type it into my calculator. Negative 6 times 2 is e to the negative 12th, times 6 times 2 is 12 to the 15, leave that in parentheses, divided by 15 factorial. Now I could write this out as 15 times 14 times 13, etc. And if you don't have a factorial button in your calculator, you will have to do that. Now I wanted to show everybody what the factorial button could look like in case you have one. It might be a little simpler instead of typing out the 15 times 14 times 13, etc., etc., etc. So here, this button is what I'll use for factorial. If your calculator has this, then you can use it as well. If not, you'll just have to write it out, all the terms multiplied from 15 down to 1. So typing this into my calculator, I'll get e to the exponent negative 12 times, first parentheses for the top of my fraction, 12 to the exponent 15 in parentheses because it's 2 digits, close the exponent parentheses, close the top fraction parentheses, divided by my 15 factorial, close parentheses, and then we get this value, rounded to 4 decimal places, is 0.0724. So just a quick recap of what we've done so far. We introduced the Poisson distribution, and we said if we know we have a Poisson distribution, then for any value of x, we can find its probability, or not any value of x, for any whole number value of x, we could find the probability x occurs using the formula you see in the middle of the screen. So if we know that we're dealing with a Poisson distribution, we have a formula for the mean, variance, and standard deviation. As before, make sure that any time or when you're making your personal formula sheet for the upcoming exam that covers this chapter, you not only have these formulas listed down, but as we've had multiple mean, variance, and standard deviation formulas that depend on what distribution you're looking at, you have it labeled that for the Poisson distribution, the mean is this. For the Poisson distribution, the variance is this. For the Poisson distribution, the standard deviation is this. So you not only have to have the formulas written down, but they have to be appropriately labeled. So the mean is lambda times t, and lambda is, remember, the average rate that they occur over the interval of time, t, or space, if we're dealing with the space kind of idea. Variance, sigma sub x squared, is lambda times t. So in this case, the mean and the variance are the same. And then we know standard deviation is always the square root of the variance. So the standard deviation, sigma sub x, is the square root of lambda times t. Let's look at our next example. The number of trees of a certain species in a certain forest is given to be a Poisson distribution. So that means automatically we've got our probability formula from the previous page of notes that works, and these three formulas now apply because it's Poisson. And we've got a mean distribution of 10 trees per acre. They ask us to round all our work to 4 decimal place. First thing it asks us is, what is the mean number of trees in a 2-acre region? Now this 10 trees per acre means there's 10 trees per single acre. That's how the rate works. It's per 1 acre. So if there's 10 trees in 1 acre, does it make sense that there should be 20 trees per 2 acres? So the mean number of trees in a 2-acre region is 20 trees. So part B asks us, what is the probability there will be exactly 18 trees in a 2-acre region? So here you're asked for probability. That makes you think of our formula from the last page when the x value in question is 18. Now remember, in the Poisson distribution, it matters what space we're interested in. So our space here is not a 1-acre region, it's a 2-acre region. So that will be our space. And one thing I want to write down really quick, the formula for the probability of the Poisson distribution is the probability at x is e to the negative lambda t times lambda t to the x over x factorial. And if we zoom out to our most recent collection of formulas, we see that this collection here, lambda t, for the Poisson distribution is exactly the mean. So we know that for a 2-acre region, the mean is 20. And that's because our rate of trees is 10 per 2-acre period of space gives us our 20. So this lambda times t, I can either rewrite it as 10 times 2, or we know it simplifies that our mean over 2 acres is 20. So then my probability that I have 18 trees is going to be e to the negative 10 times 2, or negative 20 when simplified, times 20 to the 18 over 18 factorial. Now we'll type this into our calculator. If you've got the factorial button, you can use that. If you don't, remember you'll need to carefully type in the denominator of the fraction 18 times 17 times 16 times 15 all the way down until you get to times 2 times 1. Make sure you don't miss any terms. And when we type that in, we should get a simplified decimal answer of 0.0843 continuing, rounding to 4 decimal places, that would be 0.0844. And that would be our probability. So finally, what's the standard deviation of the number of trees in a 2-acre region? I'd encourage you to look at our list of formulas at the top of this page. Identify which formula should we use here. So for standard deviation, that's our sigma sub x is the square root of lambda times t for a Poisson distribution. Here we know the distribution is 10 per acre. We've got a space of 2 acres. So this will be the square root of 20. We'll round to 4 decimal places. And we get 4.47 when rounded to 1. Now, as we've calculated the probability for the Poisson distribution, we've noticed that if we ever have we're trying to find the probability of a large value, like the probability of 18, like in our last example, typing in 18 factorial takes a bit of time. And in fact, when the number of trial is large, excuse me, I misspoke slightly. Let's start over. So here, when the number of trials is large, the binomial probability distribution, what we learned in a previous lesson, can be difficult to compute even with technology. However, if the number of trials is large, and by large we mean in this case greater than or equal to 100, and the probability that each trial could be successful is small, by small in this case we mean less than 0.1, so there's particular cutoffs for what is large in this case, what is small. The Poisson distribution, the formula that we've just been working with, can be used to approximate binomial probabilities. And this can be helpful because, like we said, when the number of trials is significantly large, binomial becomes very difficult to calculate, and in general, the Poisson formula is easier to work with. So it tells us that we can approximate binomial distributions with the Poisson formula only in the cases that the number of trials is greater than or equal to 100 and the probability of success for each of those trials is less than 0.1. So steps to use the Poisson approximation for a binomial: first, make sure is the number of trials greater than or equal to 100. If that checks out, then see, is the probability of success of each trial less than or equal to 0.1? If so, we can use the Poisson distribution to calculate it, and what we'll do is in the binomial we usually have a value p. The p replaces the lambda in the Poisson. The number of trials in the binomial will then replace the t in the Poisson formula. So in this next example, it says in the lottery game of Georgia, your probability of winning is 0.001. The game is played twice daily, so 730 games are played in a year. If you play twice a day for a year, what is the probability you win exactly twice? Now let's try to make sense of this problem. First of all, we need to check, is it binomial? And if it's not, we'll check, is it Poisson? So the 5 conditions for binomial, this was covered in a previous lecture. I'm just listing through the list. First, is there a fixed number of trials conducted? In this case, we're playing for a year, twice a day, so yeah, there's 730 trials. There's a fixed number. Every time you play, you either win or lose, so that fits condition 2. There's only success or failure as an option. Now, our probability of success is the same each time. Our probability is 0.001 every time we play, so that's condition 3. Condition 4 says the trials have to be independent, and that is true. Whatever I did the last time has no effect on this time, so the trials are independent. Finally, we're asked how many times, what's the probability we win exactly twice? The 5th condition says that you need to count the number of successes. That's what's happening here. So as we've checked all 5 conditions that were listed in a previous lecture, we know this is a binomial distribution. However, we notice in this binomial distribution, our number of trials, n, is quite large, 730. And we just see from the paragraph above that when you're doing a binomial distribution, if the n is large, specifically greater than or equal to 100, which this one is, we might want to consider Poisson if, in addition, the probability of winning is less than 0.1. Well, we've got our probability of winning. The probability of winning is 0.001, which is less than 0.1. So that condition is met. So we've met condition 1, we've met condition 2. That tells me that even though this is a binomial distribution, Since the number of trials is large and the probability is small, sufficiently so, I can approximate using the Poisson distribution. Now, if we use the Poisson approximation, it tells us that my probability becomes my lambda. So my lambda in this case is the probability 0.001. And my number of trials in becomes my t, so my t is 730. And now I just need to get the probability formula from a previous page, so let's look at that and write that down in general. So the formula for the Poisson distribution in general is e to the negative lambda t times lambda t to the x over x factorial. In this particular case, we want to win exactly twice. That's my x value. So we know lambda, we know t, we know x. We'll plug this in. The probability of winning twice is e to the negative lambda times t times lambda times t to the x value over x factorial. Now, each of these terms could be simplified. 0.0001 times 730 becomes 0.73. We can replace that. And we get e to the negative 0.73 times 0.73 squared divided by 2 factorial, which is 2 times 1. Let's type this into our calculator. E exponent to the 0.73 negative, close exponent, times 0.73 squared divided by our 2 gives us the value 0.1284. Continuing when rounded to 4 decimal places, that will be 0.1284. So the probability that we win twice in a year period playing twice daily is 0.1284. So that's it for this lesson. As always, if you have questions, don't hesitate to reach out via our campus communication and I'll be happy to answer them. Have a good day.